Before sophisticated satellites brought us vibrant images in wavelengths beyond our senses, people simply looked at the sun. Although he was not alone in his pursuit, in 1609, Galileo Galilei pioneered the use of the telescope in order to observe and record sunspots. His detailed sketches, produced over the summer in 1612, revealed that the sun was not a static orb in the sky, but a dynamic force. Galileo's solar discoveries sparked an academic interest in the sun, leading astronomers around the world to investigate how the sun shapes life on Earth. 400 years later, astronomers with increasingly complex satellite imagers investigate the origins and effects of the sunspots Galileo first observed. There must be something in a sunspot that opens up a wealth of knowledge and even more questions. Like Galileo before him, German astronomer Samuel Heinrich Schwab became fascinated with sunspots. From careful observation over 17 years, Schwab found a periodic cycling of the average number of sunspots. In the mid-1800s, he and other astronomers found that the sun has about an 11-year cycle between the times when we can observe the most and the least sunspots.
Understanding the 11-year solar cycle becomes very crucial in understanding the effects of space weather here at Earth, because it really dictates how often solar storms will occur and how strong they will be.
We often underestimate how beautiful a scientific discovery can be. When the Themis satellite fleet launched in 2007, the mission set out to investigate what triggers substorms. Substorms are atmospheric events visible in the northern hemisphere as a sudden brightening of the northern lights, or aurora borealis. One such substorm in March 2008 produced lightning-fast aurora with the energy of a moderate earthquake. NASA scientists found the answer to this mysterious behavior and massive energy in giant magnetic ropes. These can be as wide as the Earth itself, serve as conduits for solar wind particles which collide with the Earth's magnetic field, and charge the spectacular substorms and auroras. These ropes are evidence of a direct connection between the Sun and the Earth's upper atmosphere. It is when these ropes form and unravel that the highly energetic solar wind ignites the Earth's magnetic field and lights up the northern sky, providing a celestial dance that has captivated observers since ancient times. Sometimes a great discovery is a new perspective on the universe we thought we knew. As the Voyager spacecrafts near the edge of our Sun's reach, scientists are getting a new look at the expanse and shape of the solar system. Over 30 years ago, Voyager 1 and 2 set out for Jupiter, Saturn, and beyond. Now, as the twin spacecrafts explore the outer reaches some 9 billion miles away from Earth, they have crossed the heliosphere, the bubble of supersonic solar wind. However, when Voyager 2 crossed this boundary much closer to the Sun than expected, we received a picture of a squashed heliosphere rather than a round bubble. The squashed heliosphere helps scientists build up a picture of how the Sun interacts with the space outside of our solar system. The recently launched IBEX, or Interstellar Boundary Explorer, will further the study of how the solar wind interacts with the cold gas between stars. It's hard to imagine weather being more than rain on our weekend or ice on our road. But space weather can affect the globe, especially in the way we communicate and power our world. Space weather is the environmental conditions outside of our planet, originating from the massively energetic output of the Sun.
The solar wind is primarily comprised of protons and electrons. They're streaming outward from the Sun at speeds of up to 1 million miles an hour, and they are constantly bombarding the Earth's magnetic field.
Satellites have been launched to study solar wind, solar flares, coronal mass ejections, and other behaviors of the Sun. These phenomena impact our atmosphere, sometimes with devastating force.
So space weather includes power outages in high-latitude power grids, includes disruption of spacecraft, includes radiation that can harm astronauts in space.
With any weather, prediction is the goal. These missions will all add to the understanding of what it means to truly live with a star.